To the morning session. Our first speaker is Xiaoliang, who's going to talk about the emergent space-time from generalized free fields. So I will give you a kind of an advance notice of 5 minutes left. So it's technically a 40-minute plus 5 minutes.
Okay.
Thank you.
Thanks. Okay, so first I would like to thank Suvrat for the invitation. I'm very glad to give this talk remotely. Please interrupt me anytime if you have questions and if you have a mic. So this is a work that we finished last year, which was just appeared on the latest JHAP. And then there's an ongoing work after this one that's just finished. So, I will start by discussing the motivation of this work, and then the main topic is how space-time emerges from a general theory of which has a generalized free field. And then I will describe the setup and discuss the example, the main example, which is the SYK model, and then study the emergent space-time geometry for the given SYK model and the coupled SYK model. And then I will discuss some topics about hydrodynamics, which is related to this new ongoing work and other future directions. So we know that ADS-CFT is about the connection between space-time and the quantum information since the discovery of the Takayanagi formula. We have learned more and more about the relation that, like, the important role quantum information plays in the space-time. So we generally, we think that this boundary theory is a complicated, strongly correlated quantum field theory. And then there is entanglement and correlation structures in this theory, which is captured by the space-time geometry of the bulk. And this is the point of view I'm going to take. And then the question is like, how general are such concepts? So in particular, like if we go beyond the series like Xiaoliang's theory, if we look at a generic chaotic quantum many-body dynamics, is there some sense that there is an emergent geometry that characterizes the certain aspects of correlation and entanglement in this system? So if we compare, let's make a comparison between holographic duality and something I'm more familiar with. I don't know, maybe this doesn't make much sense if you are not if you are a high energy physicist, but I was by training a condensed matter theorist. So I would like to make a comparison with this mean field theory, which we use a lot in condensed matter. So like if you have a bunch of electrons and they're interacting, then we can do a mean field approximation, which means we define some kind of order parameter. For example, for a superfluid, the order parameter is a pair of fermions, and then that pair of fermions behaves like a boson, and that's the order parameter which behaves like in the long wavelength limit. It's described by a Landau kind of 5-4 theory, and that describes the theory near the phase condition. So if we look into a bit more detail, then this mean field theory gives us several different things. So if you just solve the self-consistent equation, it tells me what's the order parameter. And then for this order parameter, once the order parameter is determined, then the fermion is like a free fermion living on that background. And then so these two boxes, the blue and the purple box, are like the zeroth order for the mean field theory, right? So mean field theory means you approximate this interacting system by a free system, and the free system has this order parameter. And then when you go beyond this and look at the next order, you look at the fluctuations of the order parameter, and that gives you the collective modes, which are like the Gaussian modes. And then the whole thing works in some large n limit, because like if you don't have any large n, you can still do the mean field theory, but there is no guarantee that this will be a good approximation. But if you take a large n number of flavors, you can make this a good approximation, so that the fluctuations are suppressed by some factors of 1 over n. So that's exactly like in ADS-CFT, where we have some kind of boundary dynamics, and in certain large n limit, we get some theory that has other parameter, and I would say that what plays the role of the other parameter is the geometry, and for this geometry, if you to the leading order, if you assume it's a fixed background, then on top of that background there is the dynamics of the matter, which is like the analog of the quasi-particles in the mean field theory, and then going to the next order, when you think about fluctuations of the other parameter, you get graviton, which is like the analog of the Goldstone mode in the mean field theory. So then if we take another approximation, which is we go to long wavelength limit, we expect it should, for the right choice of boundary theory, it should reproduce gravity theories like Einstein's theory. And that's the analog of, like in the mean field theory case, you get the mean field approximation, but that doesn't give you like the field theory, like a phi-4 theory. Only if you take another limit of long wavelength limit, you get a universal theory, which is the phi-4 theory that describes the phase transition. So this structure is really very in parallel. And then the most unknown part is the middle green box. Right? We know pretty well what are the possible terms in the gravity theory. So it's similar to the phi-4 theory case, like without knowing the detail, we know what should emerge in this non-wavelength limit, but we don't know exactly the theory in the middle. So the goal of this work is to like do something similar to this mean field self-consistent calculation. It's like for a given interacting theory, we compute certain things, and then from that relate the coordinate functions of this interacting theory to something like an other parameter, which is like the background geometry. And the take-home message is that for any theory with a generalized free field, which means a field which is a boson-R fermion that satisfies the Wick theorem. For any theory with such a field, we can take the correlation function of that field as an input and map it to a bulk dynamics. And this bulk dynamics, because the method we use is based on a discrete time. So we discretize the time, and then we do this. We run our algorithm, and we get a bulk dynamics in the format of a discrete space-time, which is a quantum circuit. So if you take the continuous limit, what you get is you start with certain correlation functions of the boundary and map that to dynamics in the bulk quantum field. Map that to a free theory in the bulk. And the free theory in the bulk can be used to determine the bulk geometry. So, so this is like the relation between the interacting theory and the Bogoliubov quasi-particles on top of the other parameter, right? It's like starting with some correlation function. The correlation function itself satisfies the Wick theorem, but the theory is interacting. I will explain more about what that means. So if you have this generalized free field, then it's mapped to a free field in one higher dimension. So this can be viewed as a generalization of the HKLL approach, which is like the earliest attempt to map to define this holographic duality between boundary and bulk in the sense of mapping operators. And so the question is like, if everything in the bulk has a counterpart on the boundary, then what is the boundary, like what is the bulk operator in terms of boundary operator? And the original approach of HKLL was based on the reasoning that you have a bulk that's already known to be ADS space, and then you know the equation of motion. So if you know the equation of motion, you know how to determine the bulk value of the field from the boundary value. So then you write that in terms of this kernel, and every field is determined by an integral of fields on the boundary that's space-like separated from it. So once you find the kernel, then this is considered as an operator equation, and so that relates the boundary operator to bulk operator. What we develop is very similar to that, but with a different order of logic. So we were saying that we don't know anything about the equation of motion in the bulk because we don't assume there is a known geometry. So the only thing we know is the boundary correlation function. And then from the boundary correlation function, we determine the bulk dynamics and the bulk kernel and determine the bulk operator. So in the end, what we will get is something similar kernel, but in discretized time and space. And then, okay, so this is the take-home message. And to start, I will start by defining the generalized free field. So generalized free field just means any field that has correlation function satisfies Wick theorem. So if you write it in a more formal way, it means that you have a field chi, which is coupled. You can introduce a source term, and then the chi itself is interacting. But if you take some large n limit, and in that limit, when you integrate out the chi, you get that the source term only has a Gaussian generating function. Then you know all the correlation function of chi, which satisfies the Wick theorem. So all the higher point functions of chi is determined by two-point function, which is g, and determined by the Wick theorem. So and there is a similar thing for boson. So in the next remainder of the talk, I will be focusing on fermions because the most important example is SYK model. Okay, so one thing to emphasize is that this is a property that's determined by both the dynamics and the state. So you can have the same kind of dynamics, but if you have the wrong state, it will not work. Right? So for example, I can take an SYK model and start with the ground state or start with the thermal state, then this Wick theorem satisfied. If I start from an arbitrary state, this is not satisfied. Okay, so and another note is that this is very general, and you can study this in lattice models, and this has nothing to do with conformal symmetry. Right? So so this is one thing we hope to emphasize, that like the construction from correlation functions to the bulk free fermion dynamics really doesn't rely on anything about conformal symmetry. And then, yeah, we will take an example, which is the Sachs-Devier-Kitaev model. Maybe I will pause. Is there any questions?
No questions so far.
Okay, if not, so the Sachs-Devier-Kitaev model is a model proposed originally in the 90s by Sachs-Devier, and then Kitaev pointed out that this is related to holography. So it's a 0 + 1D model, which means it's just a bunch of fermions sitting in the same site with a non-local interaction. And there's n fermions, and they have a Q-body interaction, which is random. So it's a sum over all random selections of Q from the n, and then couple them with a random coupling strengths. So so this model has some very nice properties. So you know how to do the large n limit averaging over random j, and then compute the two-point function. So the two-point function is determined by some Springer-Dyson equation, which is just like the mean field equation, but now it's time dependent. So it's like a dynamical mean field. So and then there's many other properties that are very nice, like when you look at the fluctuations of the two-point function, which is like the connected four-point function, then that's related to the Swartian dynamics of the 1 + 1 dimensional gravity in the low temperature limit of SYK. But in this talk, we will only focus on the two-point function. So we don't really require low temperature. We are talking about a general temperature where this Springer-Dyson equation and the Wick theorem already apply. Okay, so we study SYK with a general temperature, and for example, this is like the two-point function at thermal state as a function of time. So you see this two-point function decays exponentially. So this is like just a very simple verification that this SYK has a chaotic dynamics. So the fermion will not be like evolving and oscillating back and forth, but it will have a two-point function that decays. So okay, so now let's go back to the point about generalized free field. So we know if I have a free theory, which means I have a Hamiltonian that's bilinear in the fermions, and then look at the ground state or thermal state of the theory, then it will also satisfy Wick theorem. So what's the key difference between the generalized free field like SYK and the free fermion? So the key difference is that let's start from a reference state, which is like a ground state or thermal state. If it's thermal state, you should think about it as like a purification of the thermal ensemble. So you start from that reference state and then make a one fermion excitation at time t, right? So this is chi I t, and then I goes from 1 to n. So this single fermion state spans some kind of small space, right? Some n-dimensional space in your big 2 to the n-dimensional Hilbert space. You have a small subspace, which is this single particle excitations. And then you can do this for a different time, right? You start from your reference state, you make excitations of the single fermions at a different time. If it's a free theory, then the fermions at a different time are just related by unitary. So the space of single particle state is really the same, independent from T. But the generalized free field doesn't have this property. The generalized free field, for generalized free field, if you define Vt to be the space of single particle states at a given time, then the space itself evolves at evolves in time. Because if you take T and T prime to be very different, let's say T prime minus T to be very large, then the correlation functions almost vanish, right? So these spaces almost become like orthogonal. So this is the key difference, and this difference tells you that the single particle states do not evolve into single particle states. They actually evolve to many particle states, and then the component of that remaining being single particle has a very small probability, and that's exactly the signature that the whole theory is interacting. And this plays an essential role in our construction. So it turns out that we propose this algorithm. And when you use this algorithm, it will tell you that there is no emergent bulk dimension if it's a free theory. Only if it's an interacting theory, if it has this property that Vt is not equal to Vt prime, then there is a bulk geometry. So now let me describe exactly what is this algorithm. So we start from the anti-commutator of fermion. So the anti-commutator of two fermions with different flavor and different time, we can view this as a matrix. So let's discretize the time. So T and T prime are some discrete values. So if you view I and T as one entry and J and T prime as another entry, then this is a matrix. So this matrix has an interesting property that this operator, the operator of anti-commutator, has the property that if the correlation function satisfies Wick theorem, then anti-commutator is proportional to identity, which means if you take any other operators and calculate the multi-point function, you'll find that this thing doesn't contract with anything else because the contractions all cancel. So this, you can view this as like in the space of states, like multi-particle excitations, where Wick theorem applies. This is like an operator that's proportional to identity. Okay, so then we want a bulk operator that's related to the boundary in similar way as HKLL, which means it's a linear superposition. Like there's a bulk fermion, which is a linear superposition of these boundary fermions. But if we want that, then necessarily we want the psi to satisfy the canonical anti-commutation relation. It means along a spatial cut, you would want these bulk fermions to anti-commute with each other, and on the same side, the anti-commutator is 1. Right? So that's the requirement, that's this equation. The psi anti-commutator for Z and Z prime to be space-like separated is a delta function. So that is the key condition that determines the K. So basically, mathematically, what happened is this condition that K dagger is identity, is delta function, which is identity matrix, plus the condition that K is supported in this part, right? So like, for example, if I have this bulk fermion, it will be supported in a smaller region. If I have this fermion, it's supported in a bigger region. So that converts into some triangular condition of K. So the K needs to involve the given part. Like if you go along this vertical direction, that's like going along here, like the bulk fermion from here. So the first one will be like this single boundary fermion here. And the second one will be like superposition of these two fermions. The third one is superposition with 3 fermions. And then, so it has this shape. This is like psi equals to K times chi. And the K has this shape and satisfies this equation. So these two conditions determine the K, and the KP is like the bulk fermions that coming into the boundary, and they can be determined in the same way. It's like a KP which satisfies the same equation, but it has a different shape. It has a shape that's left triangle rather than right triangle. So these can be simply determined by a QR decomposition. So other than a phase, which is like plus minus 1 sign here, which is undetermined, like you can multiply any row, you can multiply any row with a -1. It will not change any the anti-commutation relation. But other than that sign, this is completely determined.
So Xiaoliang, I have a question.
Yeah.
So you got the anti-commutator. Is there some notion that the bulk fermions also obey some simple equations of motion?
Yes, exactly. So that's what we're, so the analog of equation of motion here in discrete spacetime is this gate, these gates. So that's the key point is that after determining the kernel determines the equation of motion.
I see. And where was large N important here? Could you please explain that? Like why?
Large N is important because only in large N it's possible to have an interacting theory, but have generalized free field. So in the end, the only thing we need is generalized free field. But I think you can prove that this condition, like you have field that satisfy Wick theorem, but the fermion states at a different time, the single particle states at a different time have an non-trivial overlap, like the overlap is not 1. So the single fermion states that they are not free, right? So so it has to turn into something. But if it's not large, and I think eventually that's something that the complicated operator will come back to become simple and violate the Wick.
So if it was not large N, you'd have some complicated operator algebra, and then you would not find this kernel. Okay.
Yeah. Another way of saying this is if you, let's say if I have the Wick theorem and I have this property that VT at all different time are different, then you look at the union of the VT for all different time, you get a much bigger space, which is like the space we are talking about here. Like the bulk free theory Hilbert space is really like a union of all these VTs at different time. Or it's like generated by these single particle states. You can create multi-particle states from these single particle states. But the single particle state space is like a union of them, which is much bigger than a free theory, which only has that VT for a given time. And that space will be like in the case when the coordinate function decays, this space is like infinitely big because when you look at different time, they are all like orthogonal to each other. So if you don't have large N, that's just not possible. You can't have a space that's bigger than like the Hilbert space set of the many-body system. So that's where like the large N limit tells you, okay, if I first take a large N, then I have space for this much bigger space of free theory. Yeah. And then when you take into one like finite N corrections, I think that tells you that this approximation fails when you look at like very long time. Okay. So yeah, so the key is that, yeah, this is exactly the related to Suvrat's question. So we start from the boundary, and then the condition, the kernel is determined by the canonical anti-commutator relation of the bulk fermions. And the interesting thing is that once you determine the kernel, you can determine the dynamics because like look at let's say look at this dot here, then these fermions coming in and the fermions coming in here. I think I have a better figure. Yeah, look at here. Okay, so so the fermions coming into this gate and the fermions going out of these gates are all determined because this one is some linear superposition of these fermions, this one is some superposition of these three, and so on. So since you know the input and output, you can actually determine the gate. So we can determine this gate, and in the particular case of SYK, there is no flavor. So this gate is really just a 2x2 matrix with a gate angle theta. Okay. And then, so if you numerically calculate this, you'll find that the theta approach pi over 2 when you go deeper in the bulk. So around the thermal depth. So like when you go this way horizontally, then the gate is gradually getting more like a swap gate, like this picture. So it means because the chance that you go here and got reflected, the chance that you got reflected is given by the diagonal, right? It's like cosine theta. So that's vanishing. Like when you start here, you may get some chance to get reflected back, but once you get to here, it's almost just free flying forever. So you almost do not have any chance of getting reflected. And why is that interesting? Because that's exactly like a horizon. So that's exactly what we expect for a theory when the boundary theory is thermal state and it has a holographic deal, then the bulk has a black hole, and then you're falling into the black hole horizon. So when you fall into the black hole horizon, in the boundary time, like Schwarzschild time, you still have an infinite time before you approach horizon. But if you look at the dynamics of this particle that's crossing the horizon, in this infinite time, really nothing happens there because the proper time is like finite, right? So that's exactly what happens here. Like if you make an excitation here, which is like a single fermion, then the fermion will have some wave function, but then eventually it's going to go to this region, which is close to the horizon. And then you will see that nothing actually happens in this infinite boundary time and until it just freezes on this horizon, right? So that's exactly corresponds to the fact that the gate angle approach power 2. And that we can extract this bulk geometry by fitting the bulk dynamics with a Dirac fermion. Right? So like the analog of this free, like the free flying region is like the mass parameter is 0. So when you write the bulk like a Dirac, sorry, not Dirac, the Majorana fermion, when you write a Majorana fermion in a curved space, then you can choose this conformal flat metric in 2D. You can always choose the metric to be this form. Then the only place where the conformal factor will appear is in the mass term. So what happens near the horizon is this factor vanishes. Like in this case, it decays exponentially in the ADS Renderer case. So we can just fit this omega factor. More precisely, we fit M omega. So M omega can be determined by the gate angle theta. Right? So you have these gates, and then from the gate angle divided by the time difference delta t, you can fit what is M omega, and then compute the curvature and so on. Right? So the interesting thing is that, okay, so it's not so surprising that the coordinate function decays, right? So like, okay, the thermal state has two-bulk function decays, but that decay doesn't immediately tell you the corresponding bulk as an ADS curvature. But you do this calculation, and then this calculation can tell you that actually the bulk is an ADS that has a negative curvature when you go to the infrared region. And you can fit this, you can do some zero temperature fitting to determine what is M, so that I know R, right? Otherwise, I only know M times R. Otherwise, I only know M times omega, so I know like R over M squared. Yeah,
Sorry.
so, yeah.
To interrupt. Just to go back to your previous slide, so it was the case that beyond a point, the fermion just kept going in. Could you have a signal from, so to say, inside the horizon come out?
In principle, you can consider a state that comes from the past horizon, right? So you can consider a state which has this fermion coming in from here.
So wouldn't that be different from the usual Penrose diagram we write, or am I confused?
Penrose diagram is like this. So like, yeah, you could.
Okay, so it's
like the actual physical state is some state where I think that you don't have things coming this way, like from the past horizon. But you could also, yeah, you could certainly in your Hilbert space, you can construct a state that's having something going this here. But I don't have anything that's describing like the dynamics beyond the horizon.
Yeah, okay.
The whole thing corresponds to this wedge.
Okay, okay. Thank you.
Right. Okay, so yeah, I will quickly go through the basic ideas. So we can construct this.
I have a question.
Yeah.
So what makes the each gate Gaussian?
of the gates, because we are looking for a theory that reproduces the boundary theory, which satisfies the weak theorem. So the bulk theory also satisfies the weak theorem, and we require that the bulk fermions are canonical. So basically, we require the bulk theory to be a free fermion theory. So when I say Gaussian, it means it's free fermi. Right?
So if you want to incorporate subleading in N, then you need to partial the gates to slightly non-Gaussian.
If I consider finite N effect? Yes. So like if I consider finite 1 over N corrections on the boundary, that will correspond to the bulk gates getting non-Gaussian. And I'm not sure how exactly that works. Like we have some ideas about how to do that perturbatively. And from the quantum field theory point of view, it's like you can take the fermions coupled to JT gravity and then take this conformal choice of metric, and then you get this dilaton, and then the dilaton coupled with the fermion, and then probably this one finite N corrections corresponds to that dilaton field that has some fluctuation.
Thank you.
Okay. Yeah. So we can construct this bulk geometry, and then we can also study the state. So until this point, I didn't talk about the state. And so I just talk about, okay, there is this fermion which has this dynamics, right? So the bulk fermions moved around with these gates, which is like the fermion with the Hamiltonian. But I didn't talk about which state we are studying. And then the interesting thing is that the state is also determined because the boundary fermion has correlation functions which you can decompose into like real part and the imaginary part. The real part is like the anti-commutator, the imaginary part is the commutator. So the anti-commutator itself is sufficient to determine the dynamics. And then the commutator part determines the state. So because if you do the same linear transformation, you will map the commutator to the bulk fermion commutator. And the bulk fermion commutator is like the correlation function of the fermion, right? So because the anti-commutator is just canonical, it tells you it's a canonical fermion, but the commutator part is actually the non-trivial information in correlation function. And for a Gaussian state, the two-point function is sufficient to determine everything. So like we could start from the two-point function and compute entanglement entropy of any given region and any other kind of higher point functions. So we can actually, for example, we map the boundary theory to this bulk region, and then we can take any region, like in particular, we can take a region from the boundary to some cutoff point, and then we can compute the entropy. And so we can compute how the entropy depends on Z. And then maybe I will jump to here. Like you could compute mutual information, right? So like we can apply the same approach to a two-sided system. Like in a two-sided system, it's like a thermal field double state of SYK. Then you can consider correlation functions left to left and left to right. So, and when you construct the dynamics, you only need the anti-commutator. So you only need to do it separately for the two wedges because the anti-commutator is 0 between the two. So, okay, so you get two independent kind of dynamics, but the state is entangled. And then you know how the boundary states are entangled, so you can convert that into the bulk state, which is also entangled. So you can study like mutual information. And then the mutual information agrees very well with what you expect in the bulk in the bulk theory. So the interesting thing is that so when you have a bigger and bigger boundary region, we can study the mutual information between the boundary fermions in this time window and the time window on the other side. And that mutual information grows linearly. And if you study the bulk, you find that growth agrees very well with what you expect from conformal field theory in the UV of the bulk. And so if the bulk theory is really a free fermion CFT, not a CFT, but the free fermion with a mass, but when you look at UV, it's the same as a CFT. So these 2 points will get closer and closer to each other so that the mutual information is determined by the UV behavior of the CFT, and that exactly agrees with this numerical computation. So this is one, I think, a quite interesting point that the boundary theory itself has no conformal symmetry at all. It's just some finite temperature theory. It doesn't have a conformal symmetry. But when you look at the bulk UV is determined by the boundary IR behavior, and somehow the bulk UV has an emergent conformal symmetry. At least
So, so in the full theory, you will eventually see the saturate, right?
In what?
In the full theory, you will eventually see the
right.
saturate.
Yeah, in the actual theory, yeah, because there's finite n, so eventually it's going to separate. Yeah.
Okay.
But when you reach that region, I don't know how this quantity is defined, because this quantity is defined by like this mutual information between two bulk regions, right? So more precisely, it means that it's a mutual information between two algebras, right? The algebra made by a time interval of this side and the time interval of the other side. But these algebras are only defined in large N. So if you take finite N to start with, they're not even algebra. So
and I see, that's because you don't have an extra dimension to define the algebra, because the boundary is one dimensional.
yeah, it means that if you have finite N to start with, then take any fermion at any time, you just multiply them, then it's going to generate all the operators. So then the algebra you get will be independent from the time window. So the whole discussion here requires the limit that you first take large N, and then the algebra of operators depends on the time window. It gradually becomes bigger. In other words, only in the large N limit, there are new operators added when you increase the time window. So there are things that happens currently which are independent from things happening in the past. This is only possible in the infinite system. Yeah. Okay. So that's one thing we can study the state and entanglement. And the other thing interesting of this is that you can study the modes that cross the black hole horizon. So like we can consider correlation functions at any slice, right? We can take any 2 points and compute the correlation function. But one interesting fact is that if you look at the horizon, which means that you look at this kind of light-like cut and then take it to the limit where it becomes infinity. You look at the horizon and then you'll find that the correlation function actually is universal. Like the correlation function, the 2-point function at the horizon is kernel times the boundary 2-point function. But when you approach the horizon, everything looks like translation emerging time. So you can write everything in terms of omega, in terms of the Fourier transform, which is like for the boundary, it's a frequency, but for the horizon, it's like you can think of it as like a momentum in this light-like direction. And then there is a simplification which convert the commutator of the horizon, which relate the commutator of the horizon to ratio of the C, which is the commutator of the boundary fermion, and the A, which is the anti-commutator. So this thing turns out to be totally universal and is determined by KMS condition. So this tells you that the horizon fermion has a universal correlation function, which is, again, just confirming that your box theory really looks like a free Mariana fermion, because this is like the UV correlation function, right? This is like the horizon is like a point when you analyze the continuum to imaginary time. So it's just like, this is just saying like the correlation function along the horizon really looks like what it should be in a conformal field theory, which is a massless Mariana fermion in UV. So this is, again, this is telling you that KMS condition on the boundary, which is satisfied by thermal state, directly convert to this massless fermion behavior in the bulk. So doesn't matter whether I'm studying SYK or any deformed theory, I will get the same kind of correlation function. Okay, so yeah, so there's a lot of interesting things that can be studied in this case. For example, I can modify the coupling, right? I can introduce other kind of terms to study more richer kind of dynamics. As long as I still have this large N string Dyson equation, I will get the same kind of weak theorem. So this approach will still apply. But I can study like shock waves, right? Shock waves with negative energy, with positive energy and negative energy, right? So negative energy will give you a wormhole. You can study how the wormhole is built. Okay, so in summary, this is just a summary of this of what we did. Right? So, sorry.
Reminding you 5 minutes.
5 minutes, yeah. So thanks. So so in summary, for any theory with generalized free field, we will study the commutator and the anti-commutator, and the anti-commutator will determine the dynamics, and the commutator determines the quantum state that's evolved under the dynamics. And these two things together, if I take some kind of continuum limit, I can extract the properties of geometry from them. right? So that's kind of the general flow. And I want to emphasize that when we talk about geometry, this is really like remember that mean field theory thing. This is really like the background geometry in the large N limit. Right? So I'm not talking about like graviton, right? And that will be like coming in next order. And in this approach, there is no guarantee that these kind of fluctuations will correspond to a local dynamics like graviton, right? It could be something more exotic, and we don't expect like if I'm, because the boundary theory is so general, I don't expect like the next order is a nice local theory. But this tells you that at the level of two-point function, there is this general correspondence between boundary dynamics and bulk dynamics and bulk geometry. Okay, so so maybe one last thing I want to mention is I will skip these. We try different things at the Sitter space. We also studied the Sitter space because this is about two-point function, so I don't have to do it with a boundary. Okay, so one interesting direction we're studying in this new work is we want to apply similar reasoning to study hydrodynamics. So the key point is that hydrodynamics is about getting an effective equation of motion for a system that's chaotic. Right? So a system is chaotic, and naively, if you write down Heisenberg evolution of operators, it's going to evolve exponentially many terms. But we know in practice, you can assume the theory becomes thermalized locally, and you only need to keep track of some conserved currents, and then that gives you a certain simplified equation of motion. So we want to understand that in general, like if I have a system where I don't know what are the conserved quantities, in general, is there a way to describe hydrodynamics? And that's closely related to this holography discussion because we know like thermalization corresponds to black hole. So like we could study, for example, thermal correlation function. So now I'm not talking about anti-commutator, but I'm just talking about the two-point function. So this mathematics behind our construction, like looking for the kernel and so on, this is very general. So if you give me anything like this, which is like a norm, like a positive definite two-point like quadratic form, for anything like this, you can do the same. Like you can find the kernel which satisfies this triangular condition and satisfies this equation, and that will give you this bulk and guarantee that you're going to get a unitary bulk dynamics because of this condition, right? So the canonical anti-commutator relation is preserved at different times, so it's guaranteed. So basically, this is like the inverse problem of calculating the two-point function of a 1 + 1D boundary theory, about 1 + 1D free fermion theory. Right? So you have a 1 + 1 free fermion theory that will give you this kind of correlation function, and now we are saying you can explicitly do the inverse problem and start from the boundary correlation and determine the bulk. And why is that useful? Because then we expect the same thing as we see happens, that these bulk gates actually approach swap, right? This is also like we do it for some model, for some transfers, some 1 + 1D IT model. So here, like the boundary is 1 + 1D, so the bulk is like 2 + 1. And you look at these gates, and indeed they approach swap, right? So if they approach swap, we can do the same approximation. We can just throw away things beyond a certain line, right? So we can basically we can map the boundary, which is a totally unitary theory, to a bulk theory, which is like there is a semi-infinite reflectless path. And then that allows you to write down approximate equation of motion. But it's not in terms of equation of motion. It's like you give me several points on the boundary, and that determines the next point by a transfer matrix. So that's the discrete version of equation of motion. Right? 2 point depending the third is like taking the first derivative, second derivative, and determine the next time. So yeah, so you can see that if we get a good fitting, and then we can use this. We get a good fitting of correlation function, and we can use this to study property behaviors like energy and charge diffusion. So yeah, so this is just an animation that tells you that this transfer matrix, which is like approximate truncated dynamics of the fermion. The truncated fermion dynamics is not unitary anymore, right? But it approaches unitary, means that the eigenvalue of the transfer matrix becomes more and more like on the unit circle. But the interesting thing will be like there is always some eigenvalue that's away from the unit circle, which means that this like it looks diffusive even if the theory is actually unitary. Okay, so I think that's I will conclude here. And there are other things we can discuss. And in summary, this seems to be a general way to map an interacting theory to a free theory and identify what are these complicated dynamics that correspond to the horizon modes, which means they are not really, they are gone. They don't really affect our dynamics of simple operator. I think that's the key reason why this approach may be useful, because it tells you a way to generically identify what are these kind of complicated details that matter for the simple dynamics. Okay, thanks.
Thanks a lot, Xiaoliang. I have actually two questions, but I'll just ask one for now, which is, you know, a lot of the reason for the SYK model capturing aspects of black hole physics, etc., have to do with the Schwarzian mode, which arises, right, at low energies, which is a very universal thing. But here, I think, as you emphasized, you are sensitive to much more than that, right? You are sensitive to all the details of the G sigma, at least saddle point of the SYK model in your reconstruction of the bulk fermion. And if I'm right, in particular, your construction of the kernel, etc., depended on the saddle point value of the G field, right? If I'm right. And so my question for you was, you know, we can think of other variations of the SYK model, which also at low energies might give rise to a Schwarzian mode, but where the detailed G, you know, the 2-point correlator, etc., could differ at higher temperatures. And how much of your construction then would go through? That is it very sensitive to the exact nature of the saddle point for the G variable, or is it a sort of reasonably universal thing?
Yeah, thanks. First of all, this is not more sensitive than the discussion about Schwarzian dynamics, because this is only about two-point function. So like I started with assuming there's a weak theorem, but the whole like Schwarzian dynamics about the out of time order 4-point function, these are about the connected part of 4-point function, which is like the corrections, the one-run corrections to this story. So that has more requirements to the theory, because like you have a universal, like a maximal Lyapunov exponent of 2 pi over beta, and that's that I think that's a signature that the theory has like a graviton, right? So the theory we study here doesn't necessarily have that property. And on the other hand, as you said, the theory is sensitive to more details, because I take the whole G field and convert it to the dynamics. So for example, if I have an SYK of Q equal to 4, and then I added another term of Q equal to 8, and then the Q equal to 8 term will be irrelevant. So in long wavelength limit, you will get the same kind of dynamics, at least in low temperature. But then in the UV of the boundary, you will see a different behavior guaranteed by maybe described by the Q equal to 8. So then if you do our construction, you will see in general that will correspond to the change of the geometry, because we don't assume the geometry to be ADS. So if you have, say, some UV change near the boundary, you see this curve here, like the curvature has a divergence near the boundary, and in the bulk it approaches this ADS value, right? So if you modify the details, probably it's going to change this region near the boundary, but the bulk will be more universal. But you can also consider relevant perturbations, which will change the IR behavior. So that corresponds to like the traversable wormhole, which is like this coupled SYK model that Juan and I studied in 2018. So you can consider this bilinear coupling, and Q is bigger than 2. So this is relevant coupling. And this relevant coupling is going to change the infrared behavior. So the correlation functions now do not really decay anymore. It actually becomes oscillating if you consider the ground state of this model. So then we can still apply our approach there, because it has a larger n limit, satisfies the Ramanujan equation. But then the geometry corresponding to this case is like this picture. It's like I have two boundaries, L and R, and then actually there's no thermal path, so there's no horizon. So signal from one side will eventually go to the other side. Right? This is basically this global ADS2 geometry we talk about, which we also think that as the eternal traversable wormhole. because the two boundaries are not causally connected. So these you can reproduce you can compute, like without knowing the geometry, you can just start from the correlation functions on the boundary and then try to construct the bulk. And what you will see is that the bulk constructions terminates at some finite depth, because the bulk construction is really just extracting the orthogonal parts, right? So at every time here, you are extracting some bulk mode, which is orthogonal to everything in this boundary region. But once you go to a certain point, you'll find that I cannot extract anything orthogonal anymore, because the boundary starts to repeat itself. Like this boundary space of single particle states, in this example, they actually move periodically and come back to itself. So this bulk could have different topology, and that's nicely also incorporated also determined by the boundary correlation function.
Thank you.
Yeah, hi. I had this question right in the beginning of your talk about the generalized free fields, that if we have conformal symmetry, you can compute two-point function of those fields just by conformal symmetry. In SYK model, you can do a calculation. Do you know other models in which are neither conformal nor doable, or I mean, this is a complicated problem actually, to say what is a generalized free field in general. I just want to make that point actually.
Yeah. So basically, I think all the examples we know pretty well are like different variations of SYK model, and the SYK model itself only has this conformal symmetry asymptotically at a low temperature limit. So if we consider finite temperature SYK model, which is what we study here, like the temperature could even be infinity, right? So it doesn't. So that's already a model without conformal symmetry. And then there are generalizations. People study generalization of that in higher dimensions, like generalizations of SYK to 1+1 fermions with 4 fermion interactions. Like all these kind of large N series, this calculation should apply. But I think all the examples that I know are some kind of variations of SYK. Because if you want a dynamical mean field, like if you want the other parameter to be a local two-point function, a two-point function that's not local in time, it seems like we need to have this kind of averaging over random coupling. But there are variations of that, which is maybe, for example, you can have a boson field rather than a random coupling, and you can integrate out the boson field, can give you some kind of coupled Springer Dyson equation of the boson and fermions.
Okay. Can I ask about? So you had this slide discussing the mutual information between what I thought was the two CFTs on the left and the right, and there was this Z parameter. I got confused about this Z. Since you're looking at the boundaries, what is this Z parameter exactly?
Yeah, so this is about taking an interval on the left and then map that interval to a bulk region. So that bulk region will have a Z, the Z from 0 to Z. 0 is like the boundary.
But you have
the
different
also
on both sides, different wedge sizes on the both sides, right?
Yeah, but here I'm taking the same wedge. Yeah, so yeah, in general it could be Z1 and Z2, but here I'm taking Z and Z.
All right. Okay.
Yeah. So it's Z and Z, but then when you convert this into this bulk coordinate, so the distance between the 2 points, like this is like Z, like times 0, but spatial coordinate Z on the left wedge. This is like times 0 and spatial coordinate Z on the right wedge. And the distance between the 2 points is like exponential minus 2 pi over beta Z. It is like it decays exponentially with the increasing of Z. Because
all right, okay.
Like the horizon.
So you made a distinction between a generalized free field and really a free field.
Right.
I mean, they did not. So there are examples of such kind of duality which are known for really free fields. This is like the ON vector model and the Vasiliev theory, right? So would you say that in those theories, this intermediate step would not exist?
Yeah, that's a very interesting question. Yeah, actually, I was interested in this a long time ago. I think the answer is this. So the reason why we can do this kind of Vassiliev theory like duality is we are talking about the deal of not the fundamental field, which satisfies the weak theorem, but the bilateral field. And so the if you take an n free like the vector model, if you take the n flavor of free bosons or free fermions, and then you look at the bilinear sum over n, you look at the bilinear of that, then look at the higher point function of that field, then that doesn't satisfy the weak theorem.
Okay. So there's no bulk field which carries an ON index, but at the eventually you're going to get some Vassiliev things.
The bulk fields are all singlets, and they are interacting, but they're interacting in a very complicated way.
Yeah. Okay, I think let's thank the speaker again. Oh, you have one quick question? Yeah.
Just to try and ask maybe a variant of Shumit's question. Suppose we added a relevant perturbation which was not psi to the 8, as you were saying, irrelevant, but a psi square relevant coupling. Then in the infrared, the SYK model would flow to a free field,
Right.
literally a free field theory. What would happen to the horizon in that case?
Yeah, so I think if you are taking a low temperature, such as the ground state, yeah, because we can only talk about relevance in that case, or very low temperature. So if the free term dominates, which is basically what happens in this transversal wormhole, but I guess what you want to talk about is not like this kind of, not like the coupling, which is SU1 singlets between two different SYK, but like a single SYK with a random, maybe bilinear term.
Right.
So I think in this case, still this will dominate, and then in the long wavelength limit, it becomes a free theory. So I expect a similar thing like this termination, but maybe it's not like a sharp termination at a certain time. But I expect like you will not have a horizon because the theory will not thermalize. So like you will have a 2-1 function which gradually become dependent. Like the space of single particle states will not be independent because the theory becomes free. So yeah, but it's interesting to think of what happens there. I would guess that you get a geometry without a horizon.
Okay, I think we are badly out of time. So let's thank the speaker again.
Thank you.